and I believe we're live now, live on the YouTube. Dear guests, please turn your webcams on so that we can see your faces. And to our audience, this is once again Claudio speaking. You must be sick and tired of seeing my face every single time. Oops. I always need to silence myself. So, welcome to our ICORR Webinar number 11 on artificial sensory feedback in rehabilitation robotics. Quickly reminding you that, dear friends and colleagues, good morning, afternoon, and evening, wherever you are in the world. This is the ICORR Webinar series sponsored by the International Consortium on Rehabilitation Robotics, proud organizer of a lot of interesting events, among which this one, and the Rehab Week, well, the ICORR, so the International Conference on Rehabilitation Robotics. I use this occasion to remind you that A, subscribing to the ICORR is very cheap, and you should all do it. B, you can be an organizer to this webinar. We're always looking for people who want to organize, like in this case it was Strahinja, thank you very much for that. Number 3, this recording will be available on the YouTube later on, and you can and are invited to ask us questions through the chat. Having said that, without much further ado, let's start. The structure today is somewhat less standard. We're going to have 3 speakers speak, 20 minutes each, plus questions and answers if there's any. And then at the end, so in about 1 hour, I would say, we'll start a panel discussion, and Jose Gonzalez, who just entered the room, will be among our speakers as well. Good. Let me then read something to you about our speakers today. So our speakers are in the order that they will speak: Stanisa Raspopovic, Giacomo Valle, and Strahinja Dosen. So, Stanisa, long-time acquaintance. Stanisa Raspopovic is now a full professor at the Medical University of Vienna, Austria. Well, has been so since 2024. Previously, he was an assistant professor at Zurich at the ETH and senior scientist at EPFL in Lausanne, both of them located in Switzerland, of course. Stanisa's research interest is focused on development of innovative methods for treatment of neurologically disabled persons. In particular, he develops mechatronic systems directly interfacing the environment with the residual nervous system. Stanisa achieved translational research results of great interest in the field of neural stimulation in patients with amputation, diabetes, and pain. Substantially gifted with experience in research in neural engineering international, culminating with the award of the Science and PINS Prize in Neuromodulation 2021 and the ATH Latsis Prize in the same year. He is the grant holder of multiple very prestigious European grants, such as, for instance, the Starting Grant in 2018, well, and the Consolidator and Proof of Concepts later on in 2023. This was Stanisa Raspopovic. Giacomo Valle. Giacomo Valle is currently tenure-track assistant professor in bionics at Chalmers, that's the University of Technology in Göteborg in Sweden, leading the neural bionics lab. He has a PhD in biorobotics obtained by the Scuola Superiore Sant'Anna and joined with the EPFL, again the Technical School of Lausanne in Switzerland. And he has an MSc in bioengineering from the University of Genoa. I dare say, Giacomo, that we might have met at some point because I am originally from Genoa, Italy as well. Completed a postdoctoral training in Zurich on lower limb neuroprosthetics and University of Chicago in bidirectional BCI. I think at that time it was called Rehabilitation Institute of Chicago, and now it's the Shirley Ryan Ability Lab, right? His research focuses on developing bidirectional neuroprosthesis, restoring sensory feedback and motor control through implantable neural interface. This is one of the very few times in which we delve into invasive techniques for, well, either intent detection or feedback. Giacomo Valle has received several prestigious awards for his contribution to the field, including the FANS AJN Young Investigator Prize in 2022, and he was nominated in the Forbes 30 Under 30 in Science 2021. Then I believe, Giacomo, that you turned 30, and so welcome to the club of the senior old people. Last but absolutely not least, dear acquaintance and friend since a long time. Strahinja Dosen, now full professor at the Department of Health Science and Technology at University of Aalborg in Denmark, leading the Neuro Rehabilitation System Research Group, and also serving as visiting professor at the University of Novi Sad, located in Serbia. He holds a PhD in biomedical engineering, obtained in 2009, and has dedicated his research career to advancing rehabilitation engineering and medical robotics. His core expertise lies in human-machine interaction, myoelectric control, brain-machine interfaces, and functional electrical stimulation. I remember his pioneeristic works on ECS, actually. His work focuses on artificial sensory feedback, that's today's topic, but then as well haptics, biomimetic design, closing the loop when controlling prosthetic and assistive systems. He leads several national and international projects, and a list of his projects, well, it would be impossible right now, but one of them is Dexter Hand, together with me and someone else as well. Very good working companion as well. Interface for high bandwidth bidirectional control, Project Neuraloop, cloud connected bionics called CLIMB. This is a genius acronym, it's really wonderful. And the use of artificial intelligence to facilitate human-robot cooperation. Last but not least, number 2, of course, Jose Gonzalez Vargas, head of research in Germany at Otto Bock, where he leads the German Research Hub, focusing on translating advanced research into market-ready healthcare products. His work spans lower and upper limb prosthetics, orthotics, AI, data analytics, digital processes, and rehabilitation robotic systems, with a strong emphasis on real-world impact and clinical usability. Dr. Gonzalez Vargas is actively involved in European and German-funded research initiatives and projects, and he is a keen participant of conferences. I mean, we meet every time, as to say, and previously served as the coordinator of the Marie Skłodowska-Curie Action Project Symbionics, holding a degree in electronic engineering from the Tecnológico de Costa Rica, and completed a master's in artificial systems engineering and a PhD in medical system engineering at Chiba University in Japan. His academic career was supported by the MEXT Scholarship and the JSPS Young Researcher Fellowship. Prior to joining Otto Bock, he held a research position at Chiba University, the University of Göttingen, and the Spanish National Research Council, focusing on neural rehabilitation and assistive robotics. It's usually hard to quickly finish with the curriculum vitae of our speakers, but hey, we get you the best speakers in the world, so it's clear they always have a very, very long curriculum. So what's today's topic? There's a user and there's a robot, an assistive robot. So there's one flow of information from the user to the robot, and that's called intent detection. So you try to understand what the user wants to do. And there's a, I dare say, somewhat neglected backwards loop, the feedback loop, which is sending feelings of haptics, touch, temperature, pain, and whatever else from the device back to the user, or from the environment back to the user. And high time it was that we had a webinar on this. So I'm really, really happy to start opening the stage to our first speaker, Stanisa. Stanisa, I want to stop talking myself, and the stage is yours.
Thank you, Claudio, but your voice is so nice and you're so good in this. You can continue also my own. So, but thank you for a very kind and a really entertaining introduction, which is very important. And I'm more than pleased to be able today, if I'm able to share my screen. Yes, I'm able. Maybe. Can you see my screen? Yeah. I'm more than happy to try next up to 20 minutes to share with you some of research efforts in which we've been working on deploying the sensory feedback back to the persons that are partially or fully missing that feedback, and in order to both provide the assistance or also for the rehabilitation. And just for disclosure, what you can see in the picture is a beautiful city of Vienna with not so much beautiful building of our hospital back. I'm joking, it's one of the nicest buildings in the city. And this is where we sit, and we have a unique privilege of working back from basic science and mechatronic developments until to the patients that are on a higher floor. So we are in such a unique and beautiful ecosystem where we are trying really to deliver the solutions that can really help to the patients starting from today. And so I would start by sharing a few thoughts about the research philosophy which we share in our lab. And that it starts from understanding deeply the neurological systems with which we want to work, with which we are addressing. And we do that through the development of precise models for their behavior. Then we are able, based on these models, to understand what would be the optimized technological solution. And when I say so, it's like the device in both means of where to place the device to stimulate the nervous system and how to use it, so how to speak to the nervous system. And both can be partially answered by models, which then together with the technological developments can give us, let's call it an optimized device. And we've been deploying that with many of the speakers in the same symposium, like Giacomo and also partially Strahinja. We were doing very similar project in sensory restoration in upper lower limb prosthetics, for instance. And then, of course, as a last step in this row, one should go to the clinical assessment. And then we achieved some clinical validation, which seems promising. And we were lucky to have some achievements also for the human health benefits. But then the real science happens in a moment in which we realize what were the wrong assumptions in our models. And in this feedback loop in which we update our models and then we hopefully push the science forward. So as this topic of the seminar is about the sensory feedback, the first question that arises, why somatosensory feedback important at all? And here you can see a video from a BBC show about a man who lost his body with a rare genetic disease that disabled him from having his afferents, and particularly he is lacking, for instance, the proprioception. And as you can see, as on right, he's able to grasp the object, but with a great deal of difficulty, and he's unable to walk in a proper way. So the problem with the lack of the sensory feedback is that in reality, the movement is the sensory phenomenon. And if you think about evolution, we are made with 83% of sensory fibers in our peripheral nerves. That it means that we most probably are using those in closed loop fashion in order to move. And that inspiration plus our previous developments in amputees application, about which you're going to hear more, I believe, from Strahinja, pushed us into direction to start to exploit this physics into the patients that are missing sensory feedback. And this is where we came up with a category of patients as a spinal cord injured patients or traumatic brain injury, in which many of those patients do miss the sensory feedback alongside with the movement. And as Claudio was very nicely mentioning in his introduction, most often what clinics care about is the movement. So the idea of the clinical rehabilitation is to make patients to go basically in the most independent way out of the rehabilitation room from the hospital, being on their own foot or in a wheelchair, and to be as much as independent as possible. And very little amount of attention is given to the sensory, up to the level that when we spoke to our clinicians, they didn't have very clear ideas about the importance or the lack of the sensory feedback. So we came up and developed the system, which you can see in this slide, in which we tried to combine the soft exoskeletons, which are already traditionally used in order to rehabilitate the movement of the patients. And with this newly designed system, in which you can see on the right, we made some neurosleeves in which we properly populated these textiles with neurostimulating electrodes in order to give back possibly the sensory feedbacks to the users that have a spinal cord injury. Of course, what we need then is also the sensor, and we developed the sensors to place over the exoskeletons in order to combine that sensor information to what we are trying to stimulate back to the patients. And last but not the least, since many of the portable soft exoskeletons, they lack the power because their motors are not so big, sometimes especially in the cases of the spastic hand of the users, we would need additional help, additional force in order to open that hand. And this is why we made another part of the module, which was for the motor, the fast-like stimulation of the muscles. When all of these systems are combined together, we have a quite not trivial mechatronic system, which has to be timely and properly calibrated for each patient. But rather than me speaking, this is an explanation of our system.
It occurs, the force is recorded and transmitted to a microcontroller, which modulates the electrical stimulation back to the patient for the restoration of touch sensation and enhancing finger movement. When the participant wants to grasp an object, the movement intention is recorded from the flex sensors, which activates the motors of the exoskeleton supporting the fingers during grasping. Simultaneously, when the force is detected through the sensors, the tense is delivered, generating somatotopic sensation where the touch event occurred, in this case, the thumb. When the participant is not supported by any assistive device, he is not able to grasp the object due to the strong motor impairment. When the participant is using only the exoskeleton, he is not receiving any tactile information, failing therefore to understand when he is able to have a firm grip on the object. Only when senso-exo is used does the participant receive feedback when enough force is applied to the object to lift it over the obstacle and complete the task. When a touch event.
And so in order to achieve such a system, quite several technological developments were undertaken, and in which Andrea Cimolato and Giacomo, who is our next speaker, were really an active leaders of activities. And so we had to do something, as you can see on the screen, the system which has different model. One model is, as I was saying, about sensory feedback, called here NeuroSleeve tense model. Then there is another model stimulating the muscles, which is a fast model, and they have to be seamlessly merged and combined with the hand exoskeleton and the sensors, which were far from trivial to be integrated, because whenever we move or grasp the objects, those sensors are changing the relative orientation with respect to the object that the subject is trying to grasp. Then we proposed two parallel systems of control. One system of control which was based, if the patients had some small residual movement, we would use those flex sensors that you can see and then place them into the automatic controller of the movement. Or if the users were completely absent of any minimal motor control system, then we would use the manual switches in order to make them open and close the system. And all was integrated together with a neurostimulation and a control and power supply models. And very importantly, in order to make this NeuroSleeve model viable, we had, of course, to test the different positions and different sizes of electrodes over the different position of the nerves in the human arm. And we came up with the hotspot positions where to place those electrodes with their optimal size. And only then we were able to test all the system in closed loop. And this is more or less how the system works in everyday tasks. So you can see the user trying to grasp and drink water with just a simple and with its failure to grasp. And when the full support is there, he is, as you can see, adjusting the force he is giving, because he understands that now he's grasping enough in order to drink the water. And then also the opening is more easy action for him. Importantly, we had to make a differentiation between what, of course, happens with no support and what with only exoskeleton, and what when the user is using also the sensory part of it. And importantly, when only exo is used, he's using the flex signals here, you can see, for the control. He grasped the object without enough force, and therefore he lost the bottle. While in the last case, he clearly understands when there is enough force, and he's able to reliably grasp the bottle and take the object. So the main scientific part of this discovery was the next. A priori, when you touch in QST test that is shown in the figure A, those users with high spinal cord injuries, they do not feel specific areas of their hand, palm, or fingers. But when we stimulate them in a proper way, they are able to feel again the areas, some part of the areas they have lost. And that is due to the fact that almost every or majority of spinal cord injuries are not completely complete. So there is some spare number of fibers that are passing through the injury site, and then if you stimulate on periphery the mixed nerve strong enough, so engaging majority of those fibers, we are able to deliver back the sensation, even though rudimental and partial, which is then functionally used by our patients. And for instance, in these tasks that we developed, the patient is trying without senso-exo to grasp this virtual leg with the appropriate force and not break it. And you can see that he's, in this case, I think this is a patient with traumatic brain injury. He's failing in doing so because his sensory feedback is not adequate enough. And therefore, he's constantly breaking this mechanical switch whenever needed. Then instead, when the same user is equipped with a sensor exosystem where he does feel what he touches, as you can see here, he's able to do it without break and then to transfer the system, the egg on the other side. Of course, this system is yet experimental, investigational device, but it's giving promise that tomorrow something like this can be an assistive device helpful for everyday activities. And rather than me speaking, there is a nice video explaining our journey in this project.
The spinal cord injury disconnects the brain from the body. Simple actions like drinking water or eating dinner become very hard. Even worse, you cannot tell whether someone is touching your hand. For millions of people living with neurological injuries, this is everyday reality. We engineered a way to bring back both sensation and movement with a wearable robotic system enhanced by neurostimulation. 14 individuals with diverse neurological conditions tried it. Some of them had not felt their hand in years. Within minutes, they perceived touch again. This happens because we activate the remaining sensory pathways by precisely translating electrical signals into the nervous system's language. But to restore hand function, we also need movement. The system uses a wearable robot, called exoskeleton, to allow fingers movement, but the exo alone is not strong enough to grasp objects. So we added muscle stimulation to provide additional force. The real benefit comes from combining this motor support with a restored sensation. With robotic help alone, the bottle slips away. Instead, when we add the touch sensation, the user feels how firmly they're grasping it and adjusts their grip. Because every impairment is different, sensory and motor support are adapted to assist each person. All without surgery, helping people regain sensation, movement, and independence.
And as I promised also in the title of this presentation, this was the assistive part of using neurostimulation in robots. And on the other side, we've been since a while developing also the Rehab initiative, which is for a little bit different type of injury, which is stroke. So it's a partial brain injury. And in that category of patients, maybe if I'm able to pass on the next slide. Okay. Okay, so we use the concept of multisensory integration, which possibly you are aware of from the rubber hand illusion. So where the users are seeing the artificial hand touched in the same way like their normal hand, and since their brain basically integrates that visual information as being part of their body, because our visual is somehow dominant on our touch sensation, you can have a situation like that. When this is done in a different type of scenarios, or even with the whole body, we are able to reshape the sensation of the body position within the space. So it's like a full body illusion. And then we had an idea and hypothesis that if we properly do this multisensory intervention, we would be able to help the patients that have stroke, therefore both the injury on sensations, movement, and on their brain level. And so to do so, Valerio Rucci and our team, we developed this intervention assessment system that had on one side the virtual reality with realistic games that you're going to see in a second, plus again some type of neural sleeve that was stimulating their residual nerve, and two things were made together in properly and totally synchronized ways. Therefore, our hypothesis scientifically was that since after the stroke there are both sensory deficits, there are body representation disorders, and motor impairments, we could address in multifaceted way all of these through the electrical nerve stimulation, a full body illusion, and virtual reality. And then we wanted to make a system that is able to do all of this. And therefore, we implemented a system that you can see in this video where users are doing some training, some games, and while doing these movements, they're also feeling the touches over the objects they are having in this virtual world. And of course, this platform is then very versatile. It helps us to prepare for a clinical trial in which we had 34 chronic stroke patients, and in which in one group of first we did a pilot phase in order to show that the platform is good, repeatable, and safe, and then we did the chronic randomized feasibility trial in which one group of patients was doing the physical therapy for weeks in a same intensity, same number of games as or similar games as those that are doing our multisensory approach, and we've been comparing the outcome of one and other. So this is a very directly the result of one of our patients. So this lady, where the start of the project, you can see that she's unable to take real full independence of the arm. She needs the other arm to support the movement, and also her pinch movements are very unstable and very not repeatable. After very few days of using the platform, and of course her clinical score measured by Arat and Fugelmeier are very low. And even after like 4 days of training, you can see that she relieved from other arm. She's doing everything with her own arm, and the movement became a little bit more normal and quick. And on the final point, the clinical scores became much better only after 4 days of training. And after almost the full training, you can see that she regained full independence, and she's doing almost a correct pinch movement, which was impossible for her in the first day. And not only her, these clinical benefits were really repeatable and transferred in many of our patients. In statistically wise, they were doing better with multisensory intervention with respect to the patients that had, again, chronic stroke, but were only doing the physical therapy. So even the patients with only physical therapy were improving a little bit, but the patients with our approach were improving much more. And when we transferred this in both measurements of clinical and kinematics, we observed that they were also being able to move more quick, more smooth, and have a higher frequency of movement. And all of this was possible because the same platform at the same time is able both to rehabilitate but also to take their signals back. And again, I think this video explains that better than myself.
Your hand freezes. In a few seconds, life is no longer the same. Every year, 5 million people lose the ability to move and feel their arm after a stroke. Rehabilitation can help, but waiting lists for physiotherapy are often long. This is where multisensory comes in. You put on a headset and step into a virtual world where rehabilitation becomes an engaging game. Whether you're catching a ball, gardening, or riding a motorbike, every game is designed and chosen to train a specific arm or hand impairment. Our system goes beyond exercising. When you interact with a virtual object, electrical stimulation creates a touch sensation in your hand. The brain does not just see movement, it feels it too. With this, we are reconnecting movement with sensation. In a clinical trial, 34 stroke survivors tested our system. At first, some of them were struggling to move their arm and needed to support themselves to play. After only a few days, they were moving independently with smoothness and precision. At the same time, movements are automatically tracked, helping therapists better understand each person's progress and plan their rehabilitation path. With our system, one therapist can guide more patients at once, one day, even in their own homes, so fewer are left waiting, because recovery should not wait.
And this is really the paper that went out last week, of which we're very proud, where we have shown that if properly combined, the sensory feedback and this multisensory interaction also with the visual part can guide the motor movement rehabilitation, not only assistance. And if I manage to go to the next slide. I'm thanking you on your attention. I'm really happy to take any possible question. Thank you very much.
Stanisa, you are 12 seconds in advance on your time. This is wonderful. If all speakers in any session were like you. Good. So the proposal is now to take questions. So if there's any questions that the audience, 15 people watching right now, wants to ask, just put them in the YouTube chat. Actually, the YouTube live is about 20 seconds delayed with respect to us. So as soon as I say this, the questions should or will possibly appear. I have a remark. So I've been doing this. We have been doing this stroke rehab with just virtual reality, without neurostimulation ourselves, and we got similar. Well, results which confirm that, but not as big as yours. And I believe that's due to the stimulation which enforces or promotes the neural reorganization or regrowth of neural pathways, I guess.
Yeah, I think that is a possible reasoning behind. We did not have, resources to do the, 4 arms. That would be a dream. And now in reality, we are doing other 2 arms of this clinical trial, which are possible. But it's simply an enormous time to do such a thing with such a many number of patients, because each patient is in a program for 36 days. And my belief is that only through the correct sensorimotor integration, you are really rehabilitating, you are learning the movements again in a quickest possible way. I want to underline 2 things. This is for very specific category of chronic patients. They're lacking any type of training. So any training would make them better. This is why we compare it with the conventional one. And I do believe that the tense part, so the sensory part is very important, but we have yet to disentangle up to this level of detail.
Yeah, I do have a question in the chat by Patricia Capsi, actually a colleague, well-known colleague.
Yes,
She
also
says, thank you very much for the nice talk. I would like to know if in the EXO project, you have tried testing the learning effect of sensory feedback by removing it after some sessions.
Oh, that's a great question.
That's a really interesting question,
That's a
yes.
great question, but as described in detail in a paper, we did not have such a luxury to have so many sessions with patients. So as described there, we have 14 patients, of which 8 patients I think started all the bidirectional system, and some of them were having a really highly disabling spinal cord injury, so they could not do very many repetitions, honestly. So they were doing statistically relevant number of repetition of 3 different conditions. So no system, a robot only, and with a sensory feedback enhancement, but we couldn't study them over the days. So it was not happening that we have them over the weeks as it was in a stroke project on Nature Medicine. Of course, that's our next step, but for doing that, we need really much easy to wear system, which we didn't have, and really seamless and easy to use system. This was really proof of concept. So that question is to be addressed in the next clinical trial.
Right. Excellent. Believe we might want to move to the next talk, but this is already great food for thought and for the panel discussion. Thank you very much, Stanisa.
Thank you very much on your very kind invitation.
Well, stay in because we have to grill you after.
I'm here.
Giacomo, the stage is yours, if you please.
Yes. Sure. Yeah. Do you see the screen? Hear me well? That's great. Awesome. Let me keep the time here so I know. I try to be good as Stani. I don't know if I manage, but so thank you very much, Claudio, for the nice introduction, and Strahinja to organize this, and to be with you and presenting like the benefit of introducing the sensory feedback in robotics in general, maybe like related in particular for assistance, and Stani mentioned and very nicely also for rehabilitation. I won't give you like a little bit like another point of view on using more implantable procedure, and in particular for similar patients as Stani mentioned, like patient with spinal cord injury. And in this case, do develop bionic hands directly controlled by the brain and the intention of the user, connected with this brain interface also to restore feedback. Yeah, indeed, we have at the end different approaches, and I think the medical device field is growing to replace some or combine maybe with surgical intervention and therapies in general. But we have different type of technologies that we can use to interface with the nervous system at different levels accordingly to the type of injury, to the residual abilities of the user, and we saw. And we will see. We saw some non-invasive, and Strahinja will present some non-invasive thing for prosthetics. For prosthetics, we can go with in peripheral nerves. We did it together with Stani as well. But here we have a participant with and people with spinal cord injury where we cannot use implantable interface easily, at least in the peripheral regions and in the nerves and muscles, but one approach can go directly to go into the brain, where actually the signal and the brain is still healthy and the intentions are there. So if we are able to interact with the brain, we can actually create a bidirectional link for the robotic device. Exactly. So we are targeting for this technology people with the cervical spinal cord injury, and we know that there are many people around with limited mobility caused by these cervical lesions. And if we talk to them, one of the top priorities is for sure to have back arm and hand function, probably the top priority. But you know, the goal that we want to do here is to restore dexterous arm and hand movement. So not just you know, reaching and grasping, but something like more involving a multiple degrees of freedom. And of course, one of the approach that you have is try to reanimate the arm of the participant. So you can actually do using exos, as we saw before, functional electrical stimulation, reactivate the arm. But we are trying a slightly different approach that is still one good option for the user, that is actually to deploy this to a robotic arm. So having like a dexterous robot that can be directly controlled by the user and connected directly to the brain of the user. And since there are good robotic arms, robotic hands, we can deploy the movement to this robotic device. How we can do that? So we know that we can interface with the brain with different type of neurotechnologies, and I want to go in details on that. But our specific approach is to go very high resolution and implant microelectrode arrays into the cortex, so penetrating electrodes that can interface with the cortical region in a very selective way. So we can go around 1.5 millimeter deep into the cortex and record from a specific layers of the motor cortex, and interface also with the sensory cortex with multiple channels, and we can record even individual spikes, individual neurons, and this is very high density and very rich signal that we can use to extract as many information as possible to control this multi-degrees of freedom arm. We do this in a consortium. So I'm part of a consortium called Cortical Bionic Research Group that is a cross-institutional collaboration between University of Chicago, University of Pittsburgh, and Northwestern University. And when we have this unique opportunity of working with people with spinal cord injury, chronically implanted with microelectrode arrays in their brain, and chronically, and so we can study how to restore this function and how to create this bidirectional connection with their brain. So first of all, we need the interface, as we mentioned. So we use these BlackRock Neuroport electrodes with from 32 to 96 electrodes, and in particular, we implant two arrays of 96 channel each in the hand and arm representation in the motor cortex, and then we implant two 32 channels electrodes into the hand representation in the somatosensory cortex in Brodmann area 1. So in this way, we have a total of 256 electrodes implanted in two regions in the sensorimotor cortex, and this is our interface with the brain. Then we have pedestals through the skull that are connected to HDMI cable, where we can stream bidirectionally the information. So to create this, we need, on one hand, as Claudio mentioned at the beginning, the motor part, so the possibility to extract the motor intention of the user directly from the brain, and we use this signal from the motor cortex, because we know from non-human primates that if we record the activity of the motor cortex, you can hear the neurons firing when the monkey is reaching and grasping objects. So there is a specific pattern of activation of these neurons in different directions when the monkey is approaching objects and grasping. So we can actually read this firing rate, and we can infer from the final rate the direction and the velocity of the movement that the patient wants to do. In this way, what you can do is to decode in real time the motor intention and convert this in a control of multiple degrees of freedom of a robotic arm. You can see here, or even like a virtual arm, same concept. The patient is in the virtual scenario. We can record, convert, and move the arm. But human dexterity is much more than this. We can manipulate objects, and actually, when we touch things around us, we can extract all this tactile information and tactile features from the object that we touch. And our sensory system is encoding these tactile events in a very precise way. So we have afferent fibers that are sending all this, convert this mechanical interaction into pattern of activation. And this is interpreted by the brain as exactly the interaction that you have with the object. You can understand the force that you're applying, the features of this object in few milliseconds. And as we saw from examples, and here is another very simple from Professor Johansson in Sweden, this experiment performed by an healthy subject, light a match, very easily, few seconds possible. But if you anesthetize the fingertips and you remove these tactile sensors and biological sensors from your motor control system, your visual system is not able to replace this signal. And even a simple action like this becomes very difficult to do. So we can use the same principle as our biological system to make these bionic hands more dexterous. So the concept is to place sensors on the bionic arm and robotic arm. Then we can read in real time these sensors, convert these sensor readouts in pattern of microstimulation of the somatosensory cortex in the brain, targeted through our microelectrode interface, and then evoke sensation directly perceived on the paralyzed hand in real time, naturally, in order to promote a better control. How we can do this? So we can use what is known from neuroscience and from the human primate study and human brain mapping. We know that our body is represented in our brain. So in the primary somatosensory cortex, we have the representation of our body in the brain. So if we place electrodes in specific location in the brain, we can target the area that we want, in particular the fingertips in this case. So we can target fingertips with our microelectrode arrays, and we can implant in the part that is ventrally exposed and superficially exposed for a surgery. And so very simply, when you implant these microelectrode arrays and you stimulate from one channel, the participant will perceive a sensation in a specific part of the skin that is called projected field. So every time that we stimulate with one electrode, the subject will perceive a sensation in one location. If you change the electrode, then you change the location in the brain, the somatotopic organization, and then it's perceived in another area. So in this way, you can easily encode tactile location and contact location. So we can create this projected field map for this is an example for one participant when we cover a little bit more of D2, so the index finger, and depends by the representation of this digit into the brain, we can target better the areas that are more important during the grasping and interaction with the object, that in this case are the fingertips. So these are two examples of two different projected field maps from two participants. And when you stimulate, the subject can describe the sensation in with some terms.
This one tends to be on the tip of the index finger, and I'm getting like a slight pulsing or a tapping feeling, like if I were tapping.
And when you have a robotic hand, then the projected field maps, what you can do is to assign at each sensor on the robotic hand specific channels on the array, in order that every time that you touch the finger of the robotic hand, you can stimulate accordingly the channel that you need, and you can evoke a sensation directly in the location that you want.
Index, ring, pinky.
So here is my colleague at Pittsburgh, Rob Gown, is touching the fingers, sensor finger of the robotic hand, and every time we stimulate different channel into electrodes, into the array, and the subject perceive this sensation directly and can interpret and understand where the touch location is. The second step is, of course, force feedback, very important when you interact with objects. And what you can do is at the beginning use a very simple strategy, because more intense you stimulate, low is the force that you will evoke, low is the intensity, and you can associate with low force. High is the high force, high can be the intensity in which we stimulate. Indeed, we know the stimulation amplitude of this microstimulation is correlated linearly with the sensation intensity. So more is the amplitude that we use to microstimulate the brain, higher is the intensity perceived of the sensation. So what we can do is to actually convert the sensor readout and the pressure sensors using the sensory encoding strategies into microstimulation amplitude in order to provide a sense of force. And already with these two simple tactile features, so location and force, we can provide a better control of the bionic arm. You can see here the example. So you have on the left ICMS with feedback, and on the right without feedback, performing enriched grasp and transport task. And the movements here are faster and when the sensation is provided compared to when the sensation is missing, because the subject can interact easily, can understand how much force is putting, and is enough to lift the object and transport the object. So this is already enough, very simple feedback to have an improve of these brain control bionic arms. But if we compare this super sophisticated bionic arm with the ability that we have to interact with objects, we are still far. It's still not the same. This is because we extract much more complex set of features of touch. We can extract textures, edges, motion of surface. So this is much more complex. So how we can encode more tactile features with this microstimulation? Is this possible? Is this possible? So what we did is simply at the beginning try to embed some local features of touch into the system. So what we did is to take electrodes with projected fields aligned on the skin and stimulate simultaneously these projected fields and see if the subject was able to tell the orientation of this stimulation.
Okay, so this is more of a vertical, but it's diagonal. It's going from the pinky side to the thumb side on an angle across my finger.
So the subject is able to tell exactly the orientation of this stimulation, and there is like an axis oriented in a specific way across finger or a long finger. So we were able to encode different orientations on different digits. Here you have thumb, index, and middle finger, and we replicate also with the second participant. Then we move on to something related to motion, and see again very simply, if you have projected fields that are aligned on the skin and you activate with a specific temporal order, can you encode something moving on the skin? This is taking inspiration also from visual prosthetics.
Okay, running on these two fingers, my middle finger and my ring finger, from the tips of the fingers to the middles of the knuckles, running in this direction. So running from the fingertip down towards the palm, feeling it at the tip to the middle of my finger.
But it's movement from right here on the index finger, so that's the pinky side, going towards the tip and the thumb side. So it's going from right here on the side up to the tip of the finger.
So the subject is able to perceive this sense of motion, and also if we activate these electrodes with different temporal sequence, the subject is able to tell the different direction of movement on the fingertips very reliably. So we put as a final demonstration these movement sensations into the closed loop system. So in this case, the subject was controlling a bionic arm directly by thinking about moving and steering a wheel. And in the same time, we provided stimulation and perturbation in this case, so stimulation encoding movements in one or other direction on the fingers. And we asked the participant to react to this perturbation, adjusting the steering wheel in the opposite direction. And so this was just a proof of concept to show that these sensations are exploitable in real time together with a brain control device so that they can control, feel, and readjust. And also adding cognitive load. So we added different type of cognitive load on top of this, and the subject was still able to perform this type of task. So showing that this sensation is pretty easily to interpret, very natural, similar to what we perceive when we perceive motion. Of course, we want to go beyond that, and so one of the challenges that we are trying to face now is trying to see if biology can improve engineering and these devices. So what we do is to study how is the neural basis of touch, how touch is encoded through our biological system. So we know that when we experience a deformation of the skin, we have specific patterns of activation of our afferents. This pattern is traveling along the neural axis, and then is in your somatosensory cortex. If you have the electrode and you record the activity, you have a specific pattern of activation that is embedding all this information in a specific way. And biology evolved over thousands of years and arrived to have this code to encode perception. So what we are doing right now is we have we are lucky to have a participant that is sensate. So if we touch his hand, we can record the natural activity. So we have the ground truth of the activation. So we deliver different type of mechanical stimulation to this participant, and we record the natural activation and of the somatosensory cortex. So how the brain is encoding this information in humans, and actually these are before were possible only in non-human primates. So but now with this participant implanted, we can actually have directly neurophysiology in humans that are actually very similar to non-human primates results. So we can know how these are encoded. We can see when we touch the hand how this part of the brain is activated, how this spatiotemporal activation is when we stimulate, when we mechanically stimulate, and we can precisely see what features are encoded. And the goal that we have right now is having the natural touch instead of doing traditional ICMS, very constant stimulation and constant parameters, is to embed the spatiotemporal stimulation and spatiotemporal code that is the one of natural touch. We also work a lot in
Giacomo, your time is sort of up.
Yes, it's the last slide. So this is just to tell you that we took inspiration a lot of visual prosthetics. Visual prosthetics is also using microelectrode stimulation of V1, so primary visual cortex, to evoke phosphane and sensation, a lot in common. So we have now to take inspiration and bring the fields together in order to know more. Many people involved. Thank you all, and also our BCI pioneers and participants for this research. Thank you very much.
Just great, Giacomo. Thank you very much. So, as it happened before, if there's any questions through the chat, please ask. Do our other speakers have any questions for you, meanwhile? This is, by the way, I have a remark here. I was not involved but at DLR when Patrick van der Smacht and Donahue were doing some pioneeristic experiment in this field. You're aware of that thing? It was called BrainGate.
Yeah, of course. They started many years ago. with the first brain control cursor and arm.
So in that case, they were controlling the robotic arm. So that was intent detection, and that's I'm glad to see that you're going the other way around. So it's again closing the loop. Strahinja.
Yeah, since Claudio, since you asked us if we have questions for Giacomo. So Giacomo, thank you very much. Very exciting. So my question with these moving sensations. So what is if you have this information, what is the resolution of this movement? So for instance, if you have a fingertip, can you draw like 5 or 10 lines or just one line, going up and down?
Yes. So of course, in this case, we are a kind of limited by the number of projected fields that we have on individual digit to have a specific like patterning. But we were able to combine up to 8 channels, so 8 projected fields on the fingertips to draw letters, for example. So we actually activate one after the other, and the subject was able to tell if we were drawing a C letter or a T or an L using a property of our natural touch that is called graphesthesia. No, we can read with our touch, a sense of touch, and we are much better if we trace the letter instead of indenting the letter on the skin. So when you trace and using actually this motion encoding, you can communicate much better these patterns on the finger.
Sounds like braille reading, right?
Yeah, kind of, exactly. We are limited and doing like this with the robotic devices because we don't have electronic skin available for embedding this type of sensation, but we can only activate pressure sensors for now, one after the other.
Okay. Thank you very much. There's no questions through the chat, so I'd rather give the stage to Strahinja for our last talk.
Thank you, Claudio. So now I'm sharing. Let me know when you see it. I will also. Is that now okay? Okay, so I can try. I will also start my time. So it seems that Stanisa has sort of gave us a difficult task to be precise on time. I'm also trying to take the laser pointer. So you see the laser pointer as well, Claudio? Okay, perfect. So in this talk, I will speak about artificial sensory feedback for prosthetics, for bionic limbs, and I will focus on non-invasive methods. So this talk will be sort of an overview of different things that we have done in this field. My aim will be to actually show to the audience the potential of these non-invasive approaches. And then the actual results and details, they can be seen in the papers that I have listed on the slides. And then since Stani has shown his hospital, I also, in the meantime, added 2 sort of pictures of our hospital. We are also in the hospital. It's a new hospital. It's called the Super Hospital here in Aalborg because it's just opened and it will be also roboticized and so on. So it's a very exciting time where biomedical engineers are very close to the doctors and the patients. So I'm really looking forward to developing these networks. But let me start. So we speak about prosthetics, and I think that this is something that is quite obvious. When you lose a limb, then this is a very profound event with some dramatic consequences, both in the physical, psychological, and the social aspects of a person's life. But luckily, as you can see in the movie on the left, we can give robotic prosthesis to these people, and then these robotic prosthetic devices, they can restore some of the lost motor functions. As you can see, this person can actually grasp the objects of daily life. But then there is a problem, and the problem is that these systems, as you can see from the tasks he's performing, are quite strong. But there is no somatosensory feedback from the device to the user. So the amputees do not feel their bionic limbs. And then if you ask them, as you can see now in the movie on the right, to perform some delicate tasks with these strong systems without any feedback, this can be very difficult to the users. But then good news is that we can use an approach called sensory substitution to actually restore the lost somatosensory feedback. The idea is very simple. This is the hand, and then in the hand we have mechanoreceptors. these mechanoreceptors provide a sophisticated feedback. Once after the hand is amputated, then there is no mechanoreceptors anymore, but you get the prosthesis. And the modern devices, they're sensorized. So that means that we can read the information from these sensors, and then we can stimulate the residual limb mechanically or electrically, and then we can actually transmit this information back to the user and sort of restore the lost feedback. But what I'm doing and my group is doing, we actually, with this type of approach, with this non-invasive sensory substitution, we sacrifice a bit the naturalness of the feedback that we provide. You could see also from Stanisa, non-invasively, and especially from Giacomo, invasively, how you can actually deliver electrical stimulation that sort of restores the sensation somatotopically. So that means that the feeling is as if the sensation is coming from the limb, from the prosthesis. In our case, this is not the case. So we drop the requirement for the feedback to be somatotopic, and we also drop the requirement for the feedback to be modality matched, which means, for instance, that we communicate grasping force as vibration. These are two different physical quantities or physical variables. But once we sacrifice a bit the naturality, then we actually gain a lot in flexibility. And we gain a lot in flexibility because now it's completely open to us what we do with the skin of the residual limb. We can decide freely where to stimulate, how much to stimulate, and also which feedback variables to convey to the prosthesis user. Also, since this is a relatively straightforward method, then we can benefit from quick clinical translation. And I will give you a couple of examples that sort of emphasize this flexibility that we have with this particular approach. So the first is that we have freedom to take many stimulation channels, and we can place these stimulation channels all around the residual limb. So we can stimulate the residual limb in many points. And these are the systems that we developed in our group together with our collaborators. So for instance, this system uses an array of vibration motors that you can see here. Then in this case, we have an electrode that is placed in the socket for an upper limb prosthesis user for electrotactile stimulation. And then we have very similar system, but in this case, the electrode is placed on the residual limb of the lower limb prosthesis user, transtibial prosthesis user in this particular case. So we have many stimulation points that we can use to deliver rich stimulation profiles. And just for you to see this more concretely, this is the vibrotactile system that I've shown. That's the piece of electronics that we developed. And then this electronics connects to the prosthesis, reads the sensor data, and then the feedback controller activates vibromotors. And these vibromotors then produce dynamically changing spatio-temporal profiles of stimulation that allows us to provide a rich feedback from the prosthetic device. This is how it is mounted. We have a socket here, prosthesis, and then the vibrotactile brace or the array of motors is placed above the socket in this particular example. And then we can test the impact of feedback, as you can see here, in users in our labs. Importantly, you can see that we have a self-contained system, so we don't need any laptops or whatever. The system is actually there, and it actually is quite close to how you would use this feedback in daily life. So how we can apply these rich stimulation profiles that the systems can give us? Well, let's give one example. This is Michelangelo hand from Ottobock that you can see here. And these prosthetic devices today, they have multiple degrees of freedom. In this case, you can see on the left that the hand can rotate. And on the right, you can see that the hand can open and close. So we have 2 degrees of freedom. And since amputees do not have any feedback from the prosthesis, then if they don't look into the hand, they have no idea what is the configuration of the prosthesis. So we can provide to them artificial proprioceptive feedback so that they can actually feel the movements of the prosthesis. And this is how we can do we do it. It's a novel method that we have developed together with our colleagues from IIT. We use this array of vibromotors. You can see the array here, and we place the array around the residual limb. You can see the motors here below this band. And then you can imagine that you have a Gaussian profile above the motors. This Gaussian function above the motors, it actually provides sets the intensity of motor vibration. So essentially, when the prosthesis starts rotating, then we associate the wrist angle to the mean of the Gaussian. So as the prosthesis rotates, and you can see this on the right, as the prosthesis rotates, then this Gaussian is moving across the array of vibromotors, and this creates a sensation that rotates around the residual limb. And this rotation is congruent to the prosthesis motion. So as the prosthesis rotates, the amputee feels a sensation moving around, indicating where the prosthesis is now. And then the spread of the Gaussian also determines the smoothness of this sensation. As you can see in this example here, you have several motors active, and then you have this gradual movement across this residual limb. So it's an intuitive way, and it's also a comfortable way to provide rotation sensation. But then we can also go a step further and increase the quantity of information that we are conveying with this feedback, because we can acknowledge that this Gaussian actually has two parameters. One is the mean, and the other is the standard deviation, or the spread of the Gaussian. And the spread actually determines the number of motors that are engaged. So we can associate the mean of the Gaussian, the position of the Gaussian, as shown before, to the wrist rotation angle. And then we can associate also the spread to the hand opening. So in this particular case, when you rotate the prosthesis, you feel a sensation that rotates around the residual limb. When you start opening the prosthesis, the sensation spreads from that point in both directions. And you can see a small example here. This is the position of the hand. Then when you rotate, the same activity of the motors just shifts. And then when you open, you have more motors active. So it's a sort of an intuitive way to convey two pieces of information, both wrist rotation and hand aperture, using a single array of motors. So that's a compact solution for vibrotactile feedback about 2 degrees of freedom. And we tested this in amputees. And here you can see an illustration of the testing setup. Here we have a prosthesis user. They look into the virtual hand. The virtual hand actually sets the desired configuration. And then the amputee, the participant uses EMG pattern classification to move this real prosthesis. But they don't see the real prosthesis. They only feel the feedback that I just described about 2 degrees of freedom. And they can actually adjust the real prosthesis using only the vibrotactile feedback to the configuration shown on the screen. And of course, in the experiment, this hand is moved further behind so that they really cannot see it. It's just for the sake of the movie that we placed it here. So now you can actually take the same approach, this flexibility of stimulation with multiple channels of stimulation with the sensory substitution. You can also do something useful for the lower limb prosthesis users. In these two examples, you can see a transtibial amputee and the array of vibromotors, and transfemoral amputee with an array of vibromotors placed for the sake of the feedback. It's exactly the same system that we used in the upper limb amputees. It's exactly the same electronics and also the vibromotors. And in this particular case, what we made is we projected the pressure distribution from the sole of the prosthesis to the stimulation profile around the thigh. So you can see the insole, sensorized insole, we read the data, and then we activated the vibromotors that are actually around the residual limb. So how do we do that? Again, we leverage this flexibility of stimulation to have these dynamic, intuitive profiles. And the approach is relatively simple. These are the vibromotors. They are projected visually around the sensorized insole. So they are around the residual limb, but you now see them projected just for the sake of the drawing. Then we associate for each vibromotor the sensors from the sensorized insole with some weights. And the weight is proportional to the distance between the motor and the sensor. So each vibromotor is actually a weighted average of the signals from the sensors. The closer the sensor, the more it projects onto that vibromotor. So essentially what we get with this is that the center of pressure on the foot sole, the closer the center of pressure is to the vibromotor, the stronger the vibromotor vibrates. And this provides an information on the center of pressure in all the directions. So that's why we say it's an omnidirectional feedback. And you can see some examples here, what happens when you load the prosthesis. If you hit with the heel, and then you have this roll off, and you go towards the forefoot, you will feel the stimulation on the posterior aspect of the thigh. Then this stimulation will sort of spread all around the thigh, and then it will move into the anterior aspect of the thigh. But you can have similar intuitive profiles in all the directions, even diagonally on the foot. So we tested this approach, and when we test feedback, as you will see also later, we like to do it in a sort of clinically relevant way. So we gave this feedback to the subjects, and then we asked them to walk around our hospital building and they walked over level ground, but they also had to climb the stairs up and down. And I just highlight one result. So this is the confidence rating of the subjects, and this is actually our transfemoral amputee. The others are transtibial amputees. And you can see that in the transfemoral amputee, the confidence dramatically improved. So she feels more confident when she's walking with the feedback. And as she told us, she now knows by using this omnidirectional feedback exactly how the foot is placed on the stair. So she knows when the prosthesis is ready to, accept the weight. And essentially, she sort of can progress over the stairs with much more confidence without looking into the hand, into the leg. So this is one aspect of the flexibility. And then another thing that I told you or mentioned at the beginning is that you can also choose what to feed back to the subject, because you don't have this constraint of being natural, right? Restoring just naturally existing sensations. And I will just illustrate this with one particular example that we are also developing in the group. So let's say that we go back to upper limb prosthetics, and you want to help amputees grasp reliably. So to produce forces reliably throughout the whole range of prosthesis working range, operating range. So this is actually the pipeline. So you are generating muscle contraction. Then there is a myoelectric controller in the prosthesis generating an EMG myoelectric signal. And then this myoelectric signal is fed into the prosthesis. And finally, the prosthesis produces force. And in most conventional cases, what you will do is you will feedback, you will vibrate proportional to that force to give force information to the prosthesis user. But what we have also seen is that this EMG signal here, that is an internal signal to the prosthesis, this signal actually determines how prosthesis behaves. So this signal also anticipates the force that the prosthesis will generate. So we said, okay, let's feed back this signal to the subject in addition to the force. And if you feed back this signal to the subject, then the subject knows exactly what the prosthesis will do after closing. So it's anticipatory predictive control of force. And indeed, we have tested this approach in several different studies, and we have seen that this predictive control of force is particularly useful. For instance, it is useful when grasping compliant objects. This is where some of the conventional approaches fail, because with the compliant objects, you see the force actually through the deformation of the object. So the force feedback sometimes is not that useful. Also, this EMG feedback is quite robust to disturbances in your EMG signals. So if something happens with the electrode or electrode skin contact, since you have this EMG feedback, we vibrate, we provide information on this control signal to you, you can actually compensate for these disturbances. So if you're interested in this concept, you can follow these publications, and there are some detailed results about this approach to closing the loop. But you can do the same actually also in the lower limbs. So for instance, in a recent work that we did with Jose Gonzalez and Otto Bock within European projects in bionics, we decided, we connected to the lower limb prosthesis, and it's a sensorized prosthesis, microprocessor controlled knee. It's a C-leg. We have access to the internal states of the hand, of the leg, internal states. And we decided actually to vibrate or to provide a vibrotactile feedback on the damping of the knee. So this microprocessor knee is intelligent, and as you walk, the microprocessor knee is changing the damping from stiffening up in the flexion direction, stiffening up in the extension direction, stiffening up in both directions, and it's an internal parameter. And we decided actually to provide information about this internal parameter by transmitting dedicated stimulation profiles. So 3 stimulation profiles to the subject. So when the subject then has this information, they know when they can put the weight on the prosthesis, because when the knee stiffens up, that's an indication that they can actually make a step or climb a stair. And this user also particularly appreciated this approach to feedback as well. So you can say this is sort of not directly biological, right? But it's an internal state of the system that we reveal through the feedback, and it actually improves collaboration and cooperation between the subject and the device. And finally, since we are using these non-invasive approaches and straightforward approaches, we can actually develop a system that is fully integrated into the socket. And this is example for the upper limbs. So we put our vibration motors inside the socket here, And then we have a fully self-contained system. Electronics is in the socket, and this system can be used by amputees at home. So right now we just finalized a study where these amputee participants, they used Sense8 prosthesis with vibrotactile feedback at home for 3 months. And they periodically came to our lab, and then we evaluated the impact of feedback in a battery of different tasks, from grasping the rigid object, compliant objects, to actually grasping objects of daily life. And we are now compiling the results. But what I can say preliminary is that participants appreciated the feedback, and they helped them. The feedback helped them to actually sort of learn how to use the prosthesis, and it was useful throughout the whole period of using the feedback. This is what the results show. And finally, I will end up with a little bit of future vision. So by having this flexibility of non-invasive stimulation, where you can stimulate in many points as you want, you can actually provide something. You can make something like this. You can put electronic skin that Giacomo has mentioned on the prosthesis, and then you can use electrotactile stimulation to provide a rich tactile information from the prosthesis to the subject. And this is one example of how we do it. This example is done in collaboration with IIT and University of Genoa. We have Hannes' hand here. This is actually a sort of a skin. All these points are tactile sensors. That's on the side of the prosthesis. On the side of the user, we take the electrodes, and then we have many electrodes placed, in this particular case, it's an able-bodied subject. We place it on the forearm, but in the future, they will be placed on the residual limb. And then we associate every sensor here with an electrode pad. So when the sensor is touched, then essentially you activate the pad. So now you have all this information here from many tactile sensors transmitted as the feedback to the participant. This is how it looks like when it's fully mounted. On one side, we have the electronics that acquire the signals. On the other side, we have this multi-channel electronic stimulator. And then we are assessing this system. We have already shown that you touch the prosthesis, you move around the prosthesis, you can sort of understand through the feedback that you are receiving what happens with the prosthesis. You can also grasp different objects, you can recognize the shape of the object, and so on. But this is an ongoing work that is still to be published. And finally, we would also like to take these electrodes. It looks a little bit bulky right now, but we have a project with Technalia and Lund University where we will package this and actually put it inside the socket to get a self-contained system. Now, the resolution of that system is still something that we have to sort of investigate, right? How many sensors on the prosthesis, how many sensors in the socket, but we have some nice materials, textile materials and electrodes that integrate with textile that we can actually put into the prosthetic socket and maybe test the system. That's the vision outside of the lab. And this is just an acknowledgement slide. There are many, since it's an overview talk, there are many institutions with which we collaborate, many great people, but I couldn't mention all of them. But you have all of them in the publications that are on the slides. So thank you very much.
Wonderful. Thank you very much, Strahinja. Almost perfect timing, but all in all, we are there. Before I ask for questions for Strahinja, there's a question which arrived a little too late for Giacomo. Dr. Mark Brinton asks, did you study any limitations on the temporal delays between the movement sensations? Well, this is a very interesting question, actually.
Yeah, we did. We actually changed the temporal transition between one train and one projected field at the next one. So the delay between the stimulation of the location 1 and location B. And actually we found the timing in which you start to perceive like simultaneously. So if the two stimulation are like less than 0.5 seconds, like 0.2, they are perceiving a simultaneous activation. Then you start to perceive continuous motion. So from one to another, so apparent motion is in between 0.5 and 1 second. And then if it's more than 1 second, then you start to perceive intermittent motion, like 1 second.
Yeah, I can imagine that there's that's an ominous problem. So whenever there's too much delay, you clearly lose the feeling of agency, embodiment. I don't want to get into these terms because they're controversial. We have further questions actually. So this is for Strahinja, again from Mark Brinton. is there a learning curve to learn how to use the internal EMG signal? I know the answer here.
Yeah, so there is a learning curve, but the learning curve is actually quite quick, and it is quick because one of the principles that we always follow is, and I demonstrated this a little bit in the presentation, is that we tried to make the profiles of stimulation that are very easy to understand. So, for instance, when we communicate this internal EMG as the feedback, vibrotactile feedback to the user, we normally divide it into several levels because you don't really need an exact value of the signal. So we divide it in 5, 6 levels, and then we associate, for instance, every motor to a level. So as you increase your EMG in the prosthesis, the myoelectric signal, your motors are sequentially activated, 1, 2, 3, 4. So you quickly understand, okay, when I manipulate my muscle contraction, I can actually decide which vibromotor is active. I mean, it's very easy. And then I know the level of myoelectric signal. And the level of myoelectric signal then translates into force directly. So essentially, when you want to grasp something and you want to, for instance, exert a force level 2, you have to activate your muscle so that you feel the second vibromotor buzzing, and then you keep your muscle contraction there. The prosthesis will close and produce the level that you wanted. So we do this single session training sort of, and then you can use the prosthesis. But of course, this is for you to understand the feedback, but then to be perfect in using the prosthesis with that feedback, that takes time. And this is why we run the long-term study.
Of course. I got another question, and I guess this is for you again, Strahinja, from Erkan Kaplanolu, Bio Astlab. Those are great works. Do you have any studies on how much adding stimulus affects battery consumption?
Yeah, that's a very good question. So I don't have the right numbers for you because the electronic system has been developed by electronic expert colleagues that we have in the team. But essentially, what we do is we add. So in the socket of the prosthesis, you have electronics for controlling the prosthesis, which is the electronics from the manufacturer. And then essentially what we do, we add a piece of electronics that is the feedback controller. And that all is then powered by a battery. And then we give these prostheses to the subjects to use them at home. And essentially, I mean, the impact is there is almost no change in how fast the battery is drained with the feedback. So the consumption is not very high. Also because obviously once you close the prosthesis and you produce the force, we stop vibrating. Right? So the vibration is there only to allow you to produce the proper force. Once you produce the proper force, if there is no change in the force, we stop vibrating. So we use some tricks also to lower down the battery consumption. But
optimize the battery consumption.
Exactly. This was not a sort of this was not a factor for us. So the whole study was the home study is being developed by University of Novi Sad, Otto Bock, and us, right? And that's the.
I would add that this is the typical question which sounds trivial, and for us, the scientist, is absolutely not interesting, but then it quickly becomes interesting.
Yeah.
As you want to go to product, and this gives me the opportunity to introduce the panel discussion. And of course, Jose, you're going to be the first one to get on the grill for that. And as I promised to you offline, my first question is, after hearing these incredible, wonderful advances in somatosensory feedback, why... Okay, the naive question is, why isn't it there in your product yet? And the less naive question is probably, so you don't want to talk about stuff that is still under like company secret, but I do believe there is something coming up over there. Can you, well, actually moderate and launch some themes for discussion for this panel?
Thank you. Yeah, I mean, this is, of course, a great question. So I started my PhD a little bit more than 20 years ago, and my topic was in feedback. And at that time, we all thought this was going to be solved in 5 years, but we are still at it. So it is not as easy as it seems, and there are several factors for it. But just before I enter on this, the most important thing is that actually there are products already that have feedback. So the Vincent hand, this is a prosthetic, a multi-articular hand in Germany. It has also a vibration in the wrist area, and it produces feedback in order to allow you to know what kind of modes you are using, right? So it's not a sensation or a sensory substitution signal, but it's more kind of like an indication there. And this is something that is there. Also, you have another product, is called Saphenus, and Saphenus are putting actually vibrations within the socket in order to feedback also rollover and other information similar to what Strahinja showed with the foot sole. And this is mainly used to reduce pain for some amputees, but it also has been investigated to see if you can utilize this in order to increase awareness and so on, right? So there are some products out there, and in the past there were some products also that were trying to do this as well, but they did not really survive. And that brings me to why. And one of the reasons, first of all, is usability. So as the battery topic, for example, if you have a system that drains the battery really fast and you have to charge it a lot, then of course people are going to stop using it, right? So this is something that you have to always think about. Also, if you need to put another system on top of the systems that you have, or wear a belt, or wear something that has cables and so on. So this is of course things that people will not like to do, right? So a lot of the times people is like, if I cannot wear this in 30 seconds and don't really think about it, I will not use it. And this of course is something that for a product is quite complicated, right? So if we see what Giacomo is doing is amazing, but of course, you know, having this electrode here, this is a problem that it probably needs to be solved at some point. And there are some people trying to solve this problem, right? So this is one of the aspects of why you see this is so difficult to really translate into something that is more usable, because you do not have a straightforward way of doing it. So with Strahinja, we have been trying to see if we can integrate this within the socket so the person can just wear it and go. But of course, that also has its challenges, because then the person that is making the socket will have more hard time to make the socket, and then therefore probably they will decide, no, I will not tell my amputee to wear this, because it will take me a lot of time and I will not earn as much money as I will earn if I just make a normal socket, right? And that is also another thing that needs to be understood in this business. In this business, we as a company, as Otoboka, I don't sell to a patient. I sell to the orthopedic technician, that then he has to build his hours in order to set and fix and align the systems to that. And then therefore you need to have a lot of information from different stakeholders on how you can facilitate things so that you can optimize the margins that all the people in the value chain actually make, right? So this is something that is very specific to business, and I think that is one of the main reasons why it is difficult to translate this. The other topic is also hardware limitations. So now you see you have very nice hands that move and are dexterous, but you are lacking, for example, sensors that are reliable, that can be then utilized and reutilized and reutilized and reutilized. If you put sensors only on the fingertips, but the hand grasp with the palm, then probably the sensors are not going to measure anything. Then you're not going to get information. So there is a lot of limitations there. And if you want to then put sensors all over the palm, as Strahinja is trying to do and other researchers are trying to come up, then the sensors cost a lot of money, right? And then the costs are very, very high. And then if you want to install this in a hand, then it becomes very difficult to sell it later on. So the market for prosthetic hands is very, very small. And then therefore costs are we are very sensitive on costs, and adding a little thing to the prosthetic device also will make the business case not work, right? So hopefully this, with the humanoids and all these things, investment going on, prices are going to go down, and then maybe we will have more opportunities in the future, right? And then one thing that is very interesting, that is why we were doing this research with Strahinja as well, is the added benefit. So when we see all this research and all these things that has been done in academia, you see a very nice, very clear benefit for the user, right? They feel their fingers, they feel again, they are able to do it. But when you translate this into real life, do people really benefit significantly from it or not? And one reason for this is because a lot of prosthetic users, actually, they use the sound that the motors make and they already know what is happening. Or when they are lifting a cup, just the pressure and the torque that is exerted in the socket already give them some information. For lower limb, also pressures in the socket also, and so on and so forth. And then therefore you need to have a good, clear functional benefit added, so that then you can reimburse this, or insurance will be willing to pay more for such benefits. So these are kind of like different things on why this is so difficult, and we are of course very interested to look at this, because if we manage to increase the awareness, the confidence of people using the device, then of course this will be improved, and people will also use the device more often. Because now one problem we have is that people buy it and then they use it a couple of times, and then maybe they just use it for parties, but they don't really use it that often. And so this is things that we need to consider.
Let me interject here. I mean, how long did it take before we actually saw the first two commercial systems using what the doctors call pattern matching for intent detection? I think Co-opt was first, and then you guys were the second one. But the idea was there since 50 years before, right? There are papers in the 70s about that. And
Exactly.
I believe that at some point the technology gets so mature that you can clearly display a benefit, and so people will be buying that device rather than the other. I guess here you have the same conundrum, right? So you still need to prove that if you use somatosensory feedback, then you will sell that object rather than the other one, because it clearly benefits the users.
But even if you look at the systems like Co-op and our MyoSmart now, these is systems that are not as successfully commercially successful in terms of how much market does it cover, right? So normally you still use the two sides EMGs, and this is what has been available since the 50s. And the reason also for this is not maybe that because of the patient and the usability, but also the orthopedic technician. To install all these sensors that you have for Co-op is very difficult, and not everyone can do it. And then therefore that also minimizes the deployment of these systems as well.
Do we want to have a round of comments? Strahinja, please.
Yeah, just a quick comment on one thing that Jose has mentioned. I think it's an important thing, and actually it was important in my work as well. So it is very important to acknowledge that prosthesis users receive already something that we call intrinsic or incidental feedback. So when you speak about prosthesis control, then very often people will say it's an open loop control because there is no feedback. But in fact, that's not true, because prosthesis users very quickly learn because the brain is very capable controller. So the brain estimates the state of the system from all the sources that are available to compensate for the source that is missing. So vision, audition, socket pressure, that's all used to understand what the prosthesis is doing. And you can estimate the force, the grasping force, for instance, even the movement of the prosthesis from incidental cues. And the way I also sort of experienced this is that we had a demonstration once with an amputee, and he was using force feedback provided by us. It was an early prototype, electrotactile feedback. And there were many tasks that the amputee did with the feedback, and everything was great and nice. And then at the end, after this demo has been finished, the demo was very successful. I asked him what he thinks about the feedback that we provided. And he told me that he thinks it's nice and sort of was useful, and he could understand, the tactile information that we provided to him. But essentially, he told me, don't get disappointed. I can actually do all the tasks without feedback. And that's because it was a very experienced prosthesis user. So after that, I also understood that it's, and this is the motivation, for instance, for this EMG biofeedback or for the damping feedback from the prosthesis. So the feedback has to provide something that is not yet available to the user. So either a variable that is not available at all, like a myoelectric signal or the damping in the knee, or something that is richer than what is already available. And that's motivation from omnidirectional pressure feedback. So that's a guiding principle, at least for my group, when we are developing feedback solutions.
I can definitely see the problem. Actually, yeah. Yes, exactly. Giacomo, I wanted to ask you, your techniques are maybe the most removed so far from getting into a product because, you know, you need someone to have a permanent implant in their brain. What is your take on all this?
Yeah, no, I was listening the barriers, no, that was like for the translation in the commercialization of the sensory feedback problem. If we remove 1 second, like cortical, I mean, the solution that I presented today was mostly for people with spinal cord injury. So we are speaking about another intervention. But if we move on prosthetics, and you can target nerves and not the brain, and then is actually less invasive than of course the craniotomy. But I want to put some spice here just to challenge a little the industry as well, because we develop prototypes, but I mean, it's the industry that should bring this technology to patients as fast as possible. So you mentioned some points that I don't agree with. So for example, the first thing you mentioned that uh, so the feedback needs to provide benefit to the participant and to the user in order to be like a motivation to be added in that. But I feel my personal feeling and the research, what the research is showing is that if you don't provide a rich sensory feedback when you control a prosthetic device, this cannot become dexterous enough to be exploited. But not only for the upper limb, but even for the lower limb when dexterity, but we saw from Strahinja confidence and this type of thing. So I feel that the functionality proof is there and in particular when you have if you work like with patient and you provide this sensory feedback, there are functional benefit, there is psychological and cognitive benefit of having something that is belongs to you and you can feel sensation. And the third thing that this feedback, in particular the one invasive, provide a clear reduction of phantom limb pain that is affecting many of these individuals. So this is one thing I want to cover, like all points. And for example, you saw from results in Cybathlon, for example, where pliers and simple grippers won against articulated hands without feedback. So that they have an articulated hands, but without feedback. It's not better to have a plier. The second thing is the cost. I don't think to put sensors, pressure sensors on a prosthetic leg to detect pressure is something with like that can be like very costly as an add-on for the prosthetic. And the
Giacomo, we might want to come to the conclusion.
yeah, okay, yes, and the third thing is that I feel that the richness of the feedback is the key. So if you provide a non-invasive feedback of the status of the hand, this is not beneficial, of course, to the user. But if you provide a rich sensation of what is touching, this is actually our way to interact efficiently with the environment.
Jacob, I agree with you with all the points. As I said, I am something that I would like to see feedback there, but just the sensors. You know, when you are making a product, cost is very important. And one reason why you don't see a lot of mechatronic systems is because the costs are significantly like very, very high. So if I want to add a sensor to the hand, that sensor needs to cost €1, €10. Maybe 10 euros is already a lot of money, right? Because you need to consider all how the things is constructed, right? And then the pricing that this takes, then the certifications that it takes, the validation, the verification. So there is a lot of layers that you need to take into account that adds and adds and adds, right? And that, of course, is something that I know because I am inside there, and I know that it's difficult for outsiders to think, because when I came to the company, I thought the same, right? I said like, man, you know, this sensor costs like, you know, 20 euros or 100 euros. What is that? And it is significant, right? And that is something that is a problem, especially when you have a population that is not very high. So even mechatronic knees, which is the best mechatronic product we have, when you compare to the whole overall population, is a very small percentage, right? So then this is, of course, something that needs to be considered. And industry is a bit conservative, and that's the problem, right? Because maybe if you put it and it works, then maybe it gets more, and then more people will use it and so on, right? But then you need someone to be to bet on this and to do it, right? So this, of course, is kind of like a problem. The other thing that you mentioned about the usability and to reach dexterity, you are correct, right? So if we don't have feedback, we will not be able to do dexterous movements in a good way. The problem you have there also is that the controls currently do not allow you to do dexterous movement. So then the feedback in itself to the controls that you have, which is just grasping, is not really adding that much more to what you already can do. And that's the reason why people say, if I use my prosthetic device without feedback, it will be very similar if I use it with feedback. They don't see that benefit there. Now, if we improve the controls and you start moving each of the fingers, then we might have a case here. Then we might have a way into, okay, this feedback will then provide very specific mapping to the things that you are doing. And for that as well, just the other answer I have is, one problem is that most of the research has been doing on force feedback, on feeling, on sensation of touching. But actually, what you actually need, probably you will need besides the touching, is the proprioception. And proprioception gives you so much information that right now you do not have in terms of movements as well. And this I've seen from some implanted people that we have been working on for lower limb. It is essential to have that proprioception, and just having that proprioception reestablished, you regain a lot of this sensation without having the touch in itself. So yeah, but there are many layers that we need to discuss and see, of course, right? So but I will let the
I'd
other
like
ones
first to
talk.
hear Stanisa. Yeah.
Hey, Joe, I really like these discussions on different points, but just a couple of points of my side. First, when we did our first experiments with those stroke patients, which are significant population, unfortunately, our clinicians said to us, but sensory is not problem at all. So what they're saying, there is only a motor problem, and you will hear that for a while, right? And then we were filming the patients blindfolded that were mixing their two fingers, but because they would think that the second is the fourth finger and vice versa. Okay, so there is also a lot of misconception, I think, and also in scientific area, which we must feel. And also in a parallel track, I somehow a little bit agree with Giacomo. It's we in Europe, and this is our autocritic, because I would like that European, we increase our medical technologies capabilities. We always think very, rationally, very conservative. While in America, they're implanting dozens of persons in brains and having, that momentum of neurotechnology. So what I want to state with this is that if we don't jump into the water of following the neurotechnological things and be forefront somewhere and try to propose this novel, even to the little bit risky technologies, it's going to be as it happened for Europe in AI. We're going to be a spectator watching big powers in AI doing their job, and we have to buy their tokens. At least in medical technology, also due to the Autobock and similar companies that have a big European tradition, honestly, we have to try to thrive and give some space to the novel technology. And honestly, it's not because we were doing, I was seeing other things around the Europe, sensory feedback helping with some of your systems to the stroke patients or the spinal cord injured patients, as Giacomo was saying, can be the thing. And last but not the least, very precisely technologically and scientifically, even with the very robust and very, very limited sensations that we were giving to the patients, we were enabling some functional benefits because our brain is plastic and our capability to rehabilitate based on even limited sensory feedback when we are missing all of it, like in a spinal cord injury or in stroke, and Giacomo was speaking about a spinal cord injury, I'm speaking a lot about stroke now, it's really beneficial. And I wanted even to call my talk about the sensation is the movement. It's the basic of the movement. Last but not the least, in the recent studies on the spinal cord injury stimulation for stroke from Pittsburgh, Marco Capogrosso and team have shown that only if the patient has some residual sensory capability and we can induce it, then they're going to have to rehabilitate. Long story very short, I do believe that you are right, that we have to be very careful about what we are proposing to industry. But we also, guys, have to jump. You companies have to collaborate with us universities, giving each other opportunity to do bigger steps as properly in good example Americans are doing. And I'm speaking from European perspective because especially in this moment, it's very difficult to have the pan world combinations and collaboration. So let's try to do it. And at least in medical technology, we have really decent positioning, and that's my 5 cents about technology.
Stanisa, I think this is of course true, and that's the reason why one reason why I'm here. And it's not only Ottobock, also we are basically going everywhere, looking what everyone is doing, and we are trying to see how we can highlight the potential benefits that these technologies can have, so that you can convince people to actually put it in the product, right? So, but of course, as such big companies, there is a lot of other things that needs to be taken into account, and then therefore you need to build that. And we are open to support people. I think I'm really interested to really understand, as you said, Stanisa, there's a lot of things that are not still understood from the clinician side as well, right? And the clinicians are stakeholders. So if they say, no, we don't need feedback, then you will probably not be able to do a product that has feedback unless you have a good body of information. And then therefore there is so many factors that we need to really communicate with different stakeholders to understand the requirements, the limitations, the blocks that they have in their minds, right? And I said that because we do work with Europeans and we do work with the US people as well. So we are very much involved in both worlds, and we somehow benefit from both worlds. And even if in the US they are putting a lot of money, you still see how difficult it is for these companies and even startups to actually make it through, because this business is complicated, right? So of course, these talks here, these discussions are important, are very, very important. What you guys are doing is great, because this is really showing the baseline, what is possible, what people have not thought before. And for me, that is something that is very important that we continue and that we push.
I wanted to hear Strahinja now.
Yeah, that's just to maybe something that Giacomo said. Then I will use this as a maybe point of discussion. So when I think about the feedback, right, I see maybe one pathway that is very sort of prevalent, and it's also very logical, right? We have a prosthesis, and we would like this prosthesis to become sort of like a replacement of the lost hand. And in that sense, we would like control to be dexterous, and we would like also to provide sensory feedback that is natural. But I think that there is also another perspective that is as well valid, where we can look into the prosthesis as a sort of a tool, an assistive device. And we can then accept the reality, which is also something that Jose have said. For instance, right now we cannot control all the dexterity of the prosthesis as we would like. And in that case, I think it might be even better for the user to provide a feedback that is adapted to the control that we have. Because I think maybe inadvertently sometimes we create this expectation, even in the users, that this prosthesis will behave like your hand that you lost, which is not true. So that actually brings me to the point where Giacomo said that the feedback has to be rich. And of course, I also agree, because we also like in my group to work with rich feedback, for instance, with this electronic skin and so on. But I also think that maybe it's even more important that the feedback is smart. So sometimes you can provide a simple signal that sort of helps you to interact with the device.
Yeah.
Which maybe is not natural, like for example, damping of the prosthesis, or even myoelectric signal. I mean, for myoelectric signal in the prosthesis, you can also say that it's enhancing natural muscle proprioception and so on. But in reality, it's an internal parameter of the prosthesis that you give to the user. And that actually then is sort of matched with what the prosthesis can do, which is to grasp an object and produce a certain force. So that's just a point that I wanted to make, that both perspectives are valuable, and both perspectives, I think, are valid goals, especially the one where you are practical, looking into prosthesis as a device, might brings us out into the world sooner, creating space for something more sophisticated later, for which you need technology to mature, and you have much more risks and many more risks and so on.
This is a long conundrum in research versus innovation, right? Well, you need basic research, because then you sort of know what can be transferred, and then you need to check the transfer in order to sort of direct the more advanced research. Guys, this is almost 2 hours, so anyone wants to have a final round of
I have a question. I actually have a question from Stanisa, because Stanisa is I think you're Stani, you are in a very unique position because you worked with both types. You work with invasive technologies, you work with non-invasive technologies more recently. So what's your take? I mean, why did you shift from one to the other? I mean, what's your take on this? Which technology we should focus on, or if actually, so your opinion, because you have experience on both, sitting on both chairs.
That's a very honest and very difficult question to address. There is no single answer, yes or no, according to my opinion. I can give you a few examples. So we've been working a lot on lower limb bionic legs alongside with Giacomo, where we achieved quite pioneeristic results, in which were also health promising and which I really love. And those implants were naturally preserved. They were giving several benefits we have shown. On the other side, when we were working afterwards in a clinical trial with diabetic peripheral neuropathy, so the persons that are partially losing their sensations, and therefore they have many health problems, the clear indication is not to use the implants because their healing is much worse, and also the risk for benefit ratio is lower. So in this simple example, I can show that really depends on the population that you have of the patients and then what you would love to achieve. And recent, and not least but not last but not the least, I've been recently witnessing the efforts from Michigan and Medical University of Vienna, Professor Sederna and Professor Atzman. They're doing crazy interesting things, also in, I think, collaborations with Autobot and other companies, where they're doing real bionics, doing TMR, TSR, implanting nerves and muscles. And that's very elegant, it's beautiful. And aesthetically, patients love it, especially the patients that have high amputations. But the patients with low amputations can maybe benefit from a system as yours, which I tried, by the way, the one that you do the ring around your arm, and you can really recognize it immediately. So what I want to point out is I don't think that there is one solution for all. That's first answer. Second, it will be really targetable with respect to the patient disability, the patient's needs, and the patient's age and similar. So for instance, when you showed or somebody else, we've been showing the similar things, the system for lower limb amputees, to my opinion, they're a great system for training of patients after the amputation because they need prolonged training in order to learn how to walk. And maybe they will learn the prosthesis, and they will stop using it. So really, there is no one single answer. And especially, of course, there is one answer. If we go high into the spine or brain, then the non-invasive options are less and less. We are aware about that. But overall, there is space for different technological solutions depending on disability, patient's need, and a specific application. There's not going to be one or other like only solution. That's my 5 cents.
Well, I always tell my guys in the team, well, the beauty of research is you are allowed to explore different pathways, mix them, and if you fail, no one's going to fire you. If you go to work for a company, things are different. You may be earning more money, but then you have to deliver, and it has to work, sell, be useful, I mean, on the field.
In my department, we have certain freedom to do things. So.
Okay, right. but how many Jose Gonzalez are there in the commercial world? I wouldn't be so sure. Okay. Any final remarks, Giacomo? You've been, or Strahinja? Anyone wants to say something to close up?
I will say a few words, and then I will leave it to Giacomo as well. I just want to continue what Stanisa said. I think that's an important thing, and we also focus on that. That's also how we look into the feedback. We didn't mention this in these presentations, but I think that the feedback can be a very useful training instrument for using the prosthesis. And that's also what we sort of are observing in this home-based study, where actually, the feedback that we obtained is that when you provide this EMG feedback, then it helps users understand how the prosthesis responds to commands and how they actually generate input into that prosthetic. So prosthesis could be even an intermittent component of the system where you use it, and then when you don't need it, you shut it down, or you reactivate in situations where you need it. So this feedback as a training instrument I think it's an important aspect of investigation and research.
Very good point. Giacomo.
Yeah, no. I wanted just to say that, yeah, I agree with what Strahinja said about the two approaches. I mean, both ways are valuable. It's good to bring something to the patient as soon as possible that can help them and support them in daily life, robust. But on the other hand, I really wants to push and say to all of us that we need to dream big and point to like Luke Skywalker hand or like a very dexterous hand that is actually replacing the hand, because this is how our biological system developed over thousands of years and developed the body as we have. And then what we want to do is connect the machine to the body again, to the brain again, and be control. And if we are able to do it, and we should follow and try to achieve what our biological system is doing. So I feel, since we are mostly like, it's good to have the company perspective, of course, and what is the market is asking and the patient population. But as a researcher and scientist, we need to try to go also beyond what is the current imagination of the achievement that we can do. And I feel with the growth of neurotechnology, implantable devices, robotics, AI, and algorithms, we can now do better than what in the 70s was done with the first feedback system and 1 degree of freedom prosthetic hand.
That's a really good point. Anyone else?
That's for me to finish. So I think what Giacomo mentioned is very important. So from the academic point of view, I think that dream, targeting that future is very important, right? Because trying to answer those questions and finding those methods are going to lead us in a better way, right? So fortunately, I have been now in the industry now for 9 years. So now I think my my optimism has been a little bit go down. But it is important that that vision is there, right? And then us in industry, what we need to be doing is how we can translate steps of this vision. So as you progress, how we can transfer little steps that then we can actually provide more benefits to the patients, because at the end that is what matters, right? And I think we all got into this because we want to help people, and then the more we understand, the better products we can produce. And of course we need to look at what it is possible now, so that then the mentality, the behavior, the systems can also change, and that takes time. And then therefore we need to start working on specific steps, at least from our side, and we have to collaborate. I know that sometimes these visions from industry and academy are a bit, hitting each other, but it is important that we both understand the two positions, because the two positions are valid and are necessary. And I think that this is something that for me it is important that we see it that not as a fighting things, but as a way of, okay, we are walking to that vision, but what can we do now that the industry can actually translate? And I think I have many conversations with Strahinja about this topic, and many beers that we have drank over this. And I think this is important, because this really starts to generate things. And for us, or for me, as my position of transferring or translating technology, also it gives me also more information on how I need to talk to the business people, to the clinical people, to the sales people, to the et cetera, so that I can then start convincing all the other stakeholders, so, as Stanisa said, so that we are bold enough to actually bring something in the market that maybe doesn't seem like a good business, but in the long term, it might lead to something later on, right? So thank you very much for inviting me. This was great. I think it was very nice, and yeah.
I'm going to close by, remembering a thought I had a few years ago. The more I study this problem, specifically intent detection, but then I feel that it is a holistic problem. You have to solve the whole thing all together in order to make the whole thing progress. Feedback, intent detection, sensors, better hardware. So yeah, I mean, we are entangled in a very, very hard problem, and that means that we will be in business for a long time yet. But, we're doing our best, and our audience should be reassured about that. Thank you very much. It was a long but enthusiastic, really good webinar, and I hope to see you again shortly in any conference in the world. Thanks to the audience for the questions. See you in a couple months for the webinar number 12. The topic is yet to be decided. Bye-bye.
Thank you. Bye-bye.
Ciao.
Thank you.